This video looks at using Newton's method, and this is a technique for approximating the real zeros of a function, and it uses tangent lines to approximate the graph of the function near its x-intercepts. To see how Newton's method works, we want to consider a function f that is continuous on the closed interval a to b and differentiable on the open interval from a to b. If f of a and f of b differ in sign, then by the intermediate value theorem, f must have at least one zero in the interval a to b. And what that is indicating, if we look at some interval from a to b, recall what the intermediate value theorem is stating, if we're inside the interval and let's say if we pick some value in between and the function turns out to be positive, and then we pick another value and it turns out to be negative, well, that tells us that your function is above the x-axis and also below the x-axis in the interval from a to b. So clearly at some point, if this function is continuous, it must cross the x-axis if it's going from positive to negative. So that pretty much ensures us that we must have a zero somewhere within inside of this particular interval. So here the example we have, suppose you estimate this zero to occur at x equals x sub 1. So if we look over here, we have x sub 1. Well, first of all, here's our function, and we're trying to kind of estimate where the x-intercept is. Well, if we pick x sub 1 down here, and if we go up to the graph, we see that we have a tangent line. And Newton's method is based on the assumption that the graph of f and the tangent line at x1, f of x sub 1, both cross the x-axis at about the same point. So what we're saying is if we guess here to be x1 and we go up here to the graph and we draw a tangent line at this point, then notice the tangent line crosses the x-axis here at x sub 2. And what we're saying is this point is going to be pretty close to the zero, which we know here is actually at the point C. And what that tells us is we could actually then, if we want to continue this process, we could go down from x2 here, and we could find this point on the graph. At x2 we have a point here, and if we were to calculate the tangent line at this point, notice here we would end up with another point on the x-axis, which would be x sub 3, and notice how this point is even closer to the actual zero. So that's Newton's method here, and we could keep using this process till we get even closer, or however accurate we want to be, to the zero. So let me go through this again. You make an initial guess, and we calculate the tangent line, and if you extend the tangent line all the way down to the x-axis, we're calculating the zero of the tangent line, and that's going to be an estimate to the zero. And if we repeat the process, use x sub 2 now as our next guess, and then we could go down to the point on the graph and draw the tangent line, and if we find the zero, the x-intercept of this tangent line, it gives us the x sub 3, which you notice again is even closer to the actual zero. So you could kind of keep this process up, and you could see now again, if we were to go from this point and pick the tangent line here, notice when we draw it, it's going to be extremely close, or really close to the point C. And that's what this is explaining here. It says that because we can easily calculate the x-intercept for this tangent line, you can use it as a second and a better estimate of the zero of function f. And here's where we come up with our formula. The tangent line passes through the point x1, f of x1, and the slope would be f prime of x1, the derivative evaluated at x1. So down here, if we look at this in point slope form, the equation of the tangent line is y minus f of x1 equals f prime of x1 times x minus x sub 1. And really all this is a different notation for y equals, y minus y1 equals m times x minus x1. So this is your point slope formula, but we're using the function notation. Y minus f of x1, that's simply y1. F prime of x1, that's your slope at x1, the slope of the tangent line. And then x minus x1. And what we're saying, if we solve this for y, we get the following function below here. And what we're indicating here is we want to let y equals 0, and solving for x, we come up with the following equation. And this is how we can come up with our x-intercept here. So x is equal to x1. This is your initial guess, x of 1, minus f of x1 divided by f prime of x1. So from this initial guess, we would end up with our x sub 2, which we could use that again, as I indicated, to come up with another guess or estimate. And you can see by the graph, this is what I mentioned above. You get your tangent line, we can have another guess with x sub 2, and then we end up with x sub 3, and you could go to an x sub 4, x sub 5, as many times as you need to get as accurate to the 0 as needed. And you'll find you probably won't have to do this more than about 3 or 4 times to get pretty accurate to the 0. And that's what they're indicating here, to continue to use this formula to even make your estimate more accurate. And notice here, this repeated process is what is called Newton's method. And below here is the formula that we can use. It's x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So basically what that means, if we're looking for our initial guess, which would be x sub 1, then that would be this x sub n. So that means x sub n plus 1 would be x sub 2 is equal to x sub 1 minus f of x sub 1 over f prime of x sub 1. So then, of course, if you're looking for x sub 3, that would be equal to x sub 2 minus f of x sub 2 divided by the derivative of x sub 2. All right, so let's look at how we can apply this concept to an example here below. We're given a function, 2x squared minus 3, and they want us to use the initial guess of 1.7. So first of all, there's several things we need to calculate. We're going to need to know x sub n, f of x sub n, f prime of x sub n. So that means we need to calculate the derivative of our function, and that would simply be 4x. Okay, and now to make this easier, I'm going to show you how we can actually use our calculator as a way to come up with this formula above. And if you notice down here, I've created a chart where n, that's just our number that we're using. So we're going to start with n is 1. So that means we would have x sub 1. And we know here it says the initial guess is going to be 1.7. So that we don't have to do all these calculations by hand, we're going to plug this into the calculator. So what we're going to do now is we're going to plug in basically kind of this chart into your calculator. So to do that, first of all, we're going to use the table function. And before we go to the table, I first want you to go to second window and that's where you have your table set up. And make sure that here under the table setup that the independent is highlighted as ask. And if not, go down, simply scroll down and highlight ask and hit enter, and then the dependent variable should be auto. All right, now if you go to y equals, we want to type in our function. So the function that we had earlier here is the original function 2x squared minus 3. Okay, so that's our function, and we want to type this into y1, and then the derivative, we want to type that into y2, and then here f of x sub n over f prime of x sub n, we want to type this into y3, and we're going to do that by taking y1 divided by y2, and then in y4 we're actually going to type in x, and don't make a mistake here, you're actually going to type in the variable x minus, well, what is all of this here? All of this is y3. So we could just say this is going to be x minus y3. So that's what we want to do here. So the original function was x squared minus 3. So we would type in x squared minus 3. So there's y1. If we hit enter for y2, we want to type in the derivative. And let's see, it's 2x squared minus 3. So this would be 2x squared minus 3. And then if we look at the derivative, we said that would be 4x. So here under y2, we would type in 4x. All right, now y3, notice we said for y3 we want to type in y1 minus y2 because that's the function divided by the derivative. So we can do that. So we don't have to type all of that in. You're going to hit this VARs button here. It's right above your 3 buttons above the number 9 key. And go over to Y VARs at the top. And we want to select number 1 for function. And we want to take y1. So we're going to select 1. And then we're going to divide that by y2. So again, you would go into VARs. Scroll over to y VARs, number 1 is function, and now we select 2 for y2. So that's going to take function y1 divided by y2, so that's taking our function f of x divided by f prime of x. And then last for number 4, remember that's where we want to type in x sub n minus, so that's y sub 4 is going to be x minus y3. So make sure you type in here the variable x minus, we go into VARs, y VARs, function, and then we want to subtract y3. So now, once we go to our table, if you hit second and table, or second graph, that takes you to your table, we now can type in our values. So here, n is 1, so that's where we start. That's your first iteration. So if we plug x of 1 is equal to 1.7, so that means here on the calculator we would type in 1.7, hit enter. We end up with 2.78. So here we have 2.78. And then for y2 is 6.8. And we scroll over to y3, we get 0.40882. 0.40882. And then for y4, we get 1.2912. 1.2912. So what we've done here is we've evaluated the function, then we found the derivative of the function, and then we divided, and then we took our x value minus that division of f of x over f prime of x, and that gives us 1.2912. So there is our approximation for the zero. So when we come down for our second iteration, this would be x sub 2, then we're going to use this 1.2912. So that means we're going to go up here to the calculator and type in the 1.2912. So under x, we would type in 1.2912, and we hit enter, and we get 0.33439. And then for y2, we get 5.1648. 5.1648. And then for y3, we get 0.06474. And y4, we get 1.2265. 1.2265. So you can see here that we've gone through this twice now, and you can see that we are actually the same to one decimal place. Okay, so this is an approximation for our zero. And again, this is using Newton's method. So for example, if I was to go back here, and if we hit y equals, and I'm going to go down and highlight for y2. If I highlight the equal sign and hit enter, and if you highlight the equal sign for y3, and if I go down and highlight for y4 and hit enter, that means I'm not going to see the graph. So now I'm only going to graph 2x squared minus 3. So if we look at the graph of this function, here we have the graph of 2x squared minus 3. And if you look at the graph here, it looks like we approximated 0 to be 1.2265. And if you look, it looks like the graph crosses here about 1.2. So this is kind of what your calculator is doing. If you go to second and calculate, second trace, and we want to look at the 0, so I'm going to select number 2. Left bound, we want to move our cursor here to the left of the point. So our cursor here is to the left of this point. We can hit enter. And if I move the cursor now for the right bound, we want to move somewhere to the right of where the 0 is. Hit enter. And it says to guess, so we're going to move our cursor close to that point as we can and hit enter. And notice they give us the 0 for this function here is 1.2247449. So 1.22, that is very close. So that's what we have out to two places here, 1.22. And if you notice this Newton's method, we only calculated using 2 iterations here, going through this process twice. So this is your answer, or the approximation to your 0. Okay, and that's all it is for using Newton's method. And really, if you keep this y3 and y4 typed into your calculator, the only thing you're going to have to change with this is changing your function for y1 and the derivative of the function for y2. because the y3 and y4 is going to be the same process using Newton's method. Now again, I used the table form just to make sure that you had everything set up correctly. The real answer comes from y4. So if you wanted to go through this process again, if you wanted to come down here and do a third iteration, then you would simply take this number as 1.2265 and plug that in for x, and then you could do another calculation. And I guess if you wanted to do that, you could just simply then go to your calculator and type that in. And I need to go back and highlight my functions here. So if we go into second graph, into the table, and 1.2265, and if we scroll over to y4, we get 1.2247, and that is very accurate to what the calculator had given us earlier. All right, we have one more example here, and the example is f of x equals 1 minus 2x cubed, and they want you to use initial guess of 1. So here you have the same table set up, and I want you to go through Newton's method, and at this point you want to pause the video and see if you can work this out on your own, and then once you're done, hit resume and you can see the answers. Alright, so here's the answers to this problem, and here you notice we went through 4 iterations, and the reason we went through 4 iterations is the problem was probably asking us to make sure that we were accurate to 3 decimal places. So if you notice, we have 0.79 here and then 0.79 here, so we're accurate to 2 decimal places. So we go through the process a 4th time, we end up getting 0.793, 0.793. So we're accurate to 3 places, and actually we are accurate to 4 decimal places. So if they tell you to keep using Newton's method until you're accurate to 2 or 3 or 4 decimal places, that's what they mean. You want to have the same number matching up for 2 consecutive iterations. So here we're accurate to 4 decimal places. So once again, Newton's method here is just simply a way to approximate the zeros of your function.